So here is one question from Advanced 2025. It is from paper 1. The question is from the topic simple harmonic motion. Here in this question there is a ring of radius capital R in which a spring is kept there, and there is a disk of mass small m. This is the disk here. Its mass is small m and radius is small r. Initially this disk is in equilibrium position, and when we will displace this disk along the ring with a small displacement, then it will start doing simple harmonic motion. So ultimately we have to find out what is the value of this angular velocity when this disk will do simple harmonic motion. So we will use here the equation of motion when we will displace this disk along this ring. So I will draw the diagram here. Let us consider this is the ring, and initially this is the disk that is kept here. But when we will displace this disk in this direction, so let us assume this is the position of the disk now, such that this is the radius small r, and from the center we can connect here like this. This complete distance is capital R, right? So this angle will be equal to theta here. So we have to write down here all the forces that are acting on this disk. So what are the forces acting? One is the mg that is acting in this direction. One will be a friction force here. This is F, and we can assume this angle is also equal to theta. So this component in this direction will be mg cos theta. And also one force will be there due to the spring, since spring is connected to the disk, just like this. Then due to this displacement x, we can say here this is our displacement x, right? So there will be another force that will be acting on this disk, that is kx in this direction. Now I will make you understand here what is the value of this x. So I will again draw the diagram of this ring here. Since initially this is the position of disk and this is the new position of this disk, and from the center of this disk the spring is connected here. So we will say this disk has been shifted in this direction with the displacement of x, such that the spring got a compression of x. And if we connect the centers of this disk with the center of the ring, and this angle will be equal to theta, and we will be getting this distance from the center of the disk and to the center of ring. This distance will be equal to r minus small r. So here we can use the simple relation that theta is equal to arc length divided by radius, and arc length is equal to x divided by radius is capital R minus small r. So here x will be equal to capital R minus small r into theta. That is what the compression in the spring. Okay, so here we will be writing the equation of motion for this disk. So I will write here one force is kx and mg cos theta are acting in this downward direction, and friction force is in opposite direction. So here this kx plus mg cos theta, sorry, this force is not mg cos theta, this is mg sin theta here. This is mg sin theta. So this is mg sin theta minus this frictional force, that is equal to mass into acceleration. So this is one linear equation we have written here. So we have to replace this frictional force here. So we will be writing one more equation that is the rotational equation of motion, and we will write this rotational equation of motion about the center of the disk. So you can see here the mg force will not be providing any torque here, and friction force will be acting in this direction. If I draw the diagram, this is the disk of radius small r, right? Since mg force is acting in this direction and friction force, this is the spring force acting spring force is acting in this direction, and the friction force is acting in this direction. This is the friction force, right? So if we write the torque due to all the forces about the center of the disk, then mass is m is the mass of the disk and r is the radius. So here we will write net torque tau net, that will be equal to I alpha. Okay, and tau net we will be writing, it will be only due to this frictional force. Torque due to this spring force will be 0, and torque due to mg force will also be equal to 0. So tau net will be equal to frictional force F into perpendicular distance r, that is equal to I is what, m r square by 2, that is the moment of inertia of disk. And for pure rolling motion we can write here A is equal to r alpha about the center of this disk. So here it will be equal to A divided by alpha will be equal to A divided by r, right? So here this r will be cancelled out and this r will be cancelled out with this. So we will be getting here frictional force is equal to m A divided by 2. Okay, right. So here in equation 1 we will substitute this value, that is kx plus mg sin theta, and we will be writing here that if this theta is very small, theta is small, then we can write here this sin theta will be equal to theta. Okay, and we will also replace this value of x here. So we will write this equation again, that k into capital R minus small r into theta, right? And mg theta plus mg theta minus this frictional force is equal to ma by 2, and this is equal to mass into acceleration of this body, right? So we will simplify here, k into capital R minus small r plus mg into theta, this is equal to, we will add up all these terms here, ma by 2 plus ma, that will be equal to 3 by 2 ma. Okay, so here we have to replace this acceleration term also, since we are getting here the angular displacement equation, that angular equation of SHM. So if we replace this acceleration in terms of angular acceleration, then it will be easy for us to calculate the value of omega. So how we will replace it, that we will do from here. As we can see, this is what the disk here, this is the ring, and this is our disk. These are the two positions of the disk, and these are the lines that we are joining to the center of disk and the center of ring. And from the center of disk and the center of ring, the distance is capital R minus small r. And we can see here this disk is moving in this direction with an acceleration of a. Since this disk will do simple harmonic motion about the center of this ring, then we can clearly write that the angular acceleration alpha dash means the angular acceleration of the disk about the center of ring, and this alpha dash will be equal to how much? This will be equal to acceleration a divided by this capital R minus small r. Okay, so this acceleration will be equal to how much? Capital R minus small r into alpha dash. Okay, so we will replace this term acceleration in this equation, and we will again write this equation here. So it will be equal to k into capital R minus small r plus mg into theta, and this will be equal to 3 by 2 m, and in place of acceleration we will write capital R minus small r into this alpha dash. Okay, so here we have to write down the value of this alpha dash. So alpha dash will be equal to how much? This will be equal to this 2 by 3 m will be multiplied here. So we will multiply here 2 by 3 m, and here k into capital R minus small r, and divided by this capital R minus small r. Okay, and plus this mg divided by capital R minus small r, and into theta. Okay, since we can see here we have given the displacement in this direction, and the body the torque acting on this body in this opposite direction, so we can add a negative sign here, that this angular acceleration is in opposite direction to the displacement. So we can compare this term with the angular acceleration, that alpha is equal to minus omega square theta. Here omega is equal to the angular velocity of simple harmonic motion. So if we compare, then omega we will be getting as the under root of, we will multiply this 2 by 3 m term inside it, and this capital R minus small r will be cancelled out here, then it will be equal to 2k by 3 m, right, plus this m will be cancelled out here, plus 2z divided by 3m, sorry, m is cancelled out, capital R minus small r. Okay, so this is the answer we are getting, and this type of answer we have to match in the option. So here the answer we will be getting is the option number A, that is the correct answer. 2 by 3 z divided by capital R minus small r, 2 by 3, so this is the correct answer we are getting here. So option A is the correct.